Hello everyone, my name is Kumar Mantha, and today I'll be presenting my project titled Improving Heart Disease Diagnosis Accuracy Using Local Cascade Ensemble, or LCE in short. This project was a part of my data mining course. The focus of this work is on predicting heart disease more accurately by comparing traditional models like logistical regression and random forest with a more advanced method called as local cascade ensemble. So uh, I, this is not a deployment project. This is more of a research project. I'm just using the heart disease diagnosis dataset as a medium to explain what local cascade ensemble does and how it does. So coming to the background and motivation of the project. So why heart disease prediction? So heart disease remains one of the biggest causes of death worldwide. Early diagnosis is absolutely critical because it can signify and significantly reduce risks and improve treatment outcomes. However, clinical diagnosis often relies on manual assessments, and it can be subjected to human error. This is where machine learning can help us. Machine learning can usually identify patterns in large data sets and reveal risk factors that doctors may not catch early. So my main motivation was to evaluate whether an advanced ensemble model, specifically LCE, can outperform the common machine learning models on predicting heart disease, especially under an imbalanced dataset. So going to the next slide, which is the dataset overview. I found this dataset in the Kaggle website. So uh, it is under the name of Indicators of Heart Disease Dataset 2022 updated. So there are two datasets in here, one of 2020 model and one of 2022. So the 2020 model had a target variable called as heart disease, but the 2022 model didn't have any. So I had to perform some feature engineering, more of it later. But coming to the dataset overview, we had 320,000 observations with 18 variables or columns. And all of this, some of them were numerical and some of them were categorical. So the key features in this data set were demographics such as age, sex, race, and some categorical values such as smoking, alcohol, physical activity, and some numerical variables such as BMI, sleep, mental health, physical. So the challenges in this data set were, the major challenge was this was imbalanced as 88.5% of the samples had no heart disease, while only 11.5% had. That means models may achieve high accuracy just by predicting no most of the time, which is misleading. So coming to the next slide, which is data preparation and feature engineering. So here in pre-processing, I have removed all the duplicate values, handled the missing values, applied one hot code encoding to all categorical features, and standardized continuous features. The dataset was also split into 80-20 using stratification to maintain class ratios. Also, another important step was creating a clean target variable. So the dataset originally had three separate columns, which was had heart attack, had angina, had stroke. So I combined all three of them using logical OR to form one clear variable called as heart disease, which becomes our new variable, target variable. So I also removed the original columns so that the model wouldn't accidentally learn the diagnosis directly from there. This ensured cleaner and more realistic prediction performance. So coming to the exploratory data analysis, or EDA for short. So several patterns appeared. Firstly, the class imbalance was clearly visible. The no heart disease class dominated in the dataset. This means we have to be very careful when interpreting the accuracy. Secondly, most numeric features such as weight, BMI, and sleep hours followed roughly normal or skewed distributions. Thirdly, the correlations between features were very low. This suggests that the simple linear models will struggle to capture the relationships between the variables as compared to more powerful ensemble methods. Finally, the categorical features like general health, smoking status, and physical activity also showed uneven distributions across the categories. Now we'll come to the machine learning models which are used in this. So there are only three models here. I just wanted to use logistic regression as a regression model, also a tree-based model, random forest here, and lastly LCE. I just want to compare the basic models with LCE just to see how it works. So as we know, linear logistic regression is a simple baseline model that is interpretable and fast. Similarly, random forest is the most powerful and capture nonlinear relationships. And the final one is the LCE model, which is the most advanced and quite recent. It uses multiple stages where each stage focuses on correcting the mistakes of the previous one. It's so the hard to classify sample get progressively more attention. So this model is especially effective when the positive class is rare, as is in our data set. So coming to its architecture, we will be talking about LC's architecture. So how it works. So imagine LC as a tree-based model, but in every node there is another tree. So at each stage, a classifier receives the data and it tries to detect the positive examples. So if it misclassifies something, the sample gets passed on to the next stage and the negative samples get filtered out early, while difficult samples move on forward. So each stage output probability predictions and the final predictions is average of all stages. This helps the model to focus more on the minority class and reduces false negative. LC is also computationally cheaper than training one big model because each stage handles a smaller amount of data. So, although I'm saying it is computationally cheaper, it does take a lot of time because we are basically putting all the models inside one tree and running it. But in the next slide, I'll explain why I'm saying it is computationally cheaper. Going to the next slide, now we will be talking about the experimental results which we got from. So I ran all these three models on the same data set with the same after performing all the pre-processing. So as you can see, the accuracy of all three models is similar. Uh, that being said, let's just talk about logistic regression first. So it performed reasonably well on majority class, but detected very few heart disease cases. Uh, also, Also, random forest did slightly worse compared to logistic regression as it predicted zero samples of heart diseases, giving it a recall of zero of minority class. As you can see, class 1 is the class where people had the heart disease, and I'm only showcasing this because it is a minority class. So finally coming to LCE, so it detected more minority class samples than the other two models, which is why its precision is higher than both of the other models. Uh, while it is still low, but it is better than both the models. But compared to random forest, which detected none, LCE clearly has done much better. So as I said in the last slide that it is computationally cheaper. So I ran logistic regression for a lot of n estimators, and in the random forest, as I said, the nodes were the max depth was increased to a lot, and there were many splits, but LCE was only ran for two stages, so which showcases why it is really powerful as it really caught up to the other two models uh, just in two stages. So imagine if proper training and hyperparameter tuning would boost the accuracy really well. So now we'll be discussing on best models. So it is not a surprise the whole PPT is named after LCE, so LCE performed best. So why it performed best? Because it detects the minority class. Unlike random forest, it is competitive against the accuracy as it retained the accuracy uh, compared to the logistic regression and the random model. So there is also a strong potential for improvement by adding more cascade layers and tuning the hyperparameters or applying SMOTE and class weighting methods. So we can significantly increase the recall of the minority class. This makes LCE highly suitable for real-world healthcare applications where detecting the rare positive cases rather than maximizing the accuracy uh, is most crucial factor. So coming to the conclusion of this presentation, I'd just like to say this project demonstrated the importance of using the advanced ensemble methods for more imbalanced medical data, while logistic regression and random forest perform adequately for the majority class. They struggled with the minority detection. So the LCE offers a balanced combination of accuracy, efficiency, and ability to detect the rare events. With additional cascade layers and class weighting and hyperparameter tuning, LCE could be strengthened even further, potentially becoming a strong tool for early heart disease prediction. So with this, I'd like to conclude my presentation. Thank you.